Okay. Yeah. So yeah, thanks for the introduction already. So I don't have to basically do this myself. I'm part of the Forest Research Foundation as a scholar. So I've been supported by the foundation throughout my PhD candidature, and I'm now reaching the end of the candidature on the topic of electricity distribution networks and how we can use evolutionary algorithm as a tool to plan those networks, especially under the consideration also of restricted areas and further constraints. Now, this talk is mainly structured around my PhD thesis, and I will talk about electricity distribution networks, but I think that the approaches that I've been using can be applied to a lot of other areas as well. So yeah, just keep that in mind when listening to the talk and when I talk about electricity distribution networks. Okay, so let's start. Okay, so typically when we look at electricity networks, we have a centralized generation, and we have some kind of usually large scale generation source, and we have an interconnected system. So consumers get the electricity supply through the transmission and distribution network, and everyone is interconnected we have one interconnected infrastructure in one system. So this is what is currently also installed in main parts in remote areas. But especially when we look at remote and rural areas, there are some challenges with the current approach, or with the typical or traditional approach of planning electricity networks. So, for example, if you look at Australia, for example, there are a couple of areas where we have only very few consumers spread over a large, basically large area. So we have a really low electricity consumer density, and those are typically connected then through very long power lines, sometimes reaching over hundreds of kilometers, and that comes with a very high cost per consumer. And this network is often also prone to several risks and hard to maintain when we look at this infrastructure. So some facts maybe because I'm studying in Western Australia, so I'm more familiar with the Western Australian network. We have our network around Perth, but also including some remote areas operated by Western Power. And there's roughly 1 million consumers in this network, spanning over 250 square kilometers, and we have around 100,000 kilometers of power lines in this system. And now the average electricity bill, according to Western Power, is constituted by 50% of this average electricity bill comes from our network and infrastructure costs. And especially considering remote areas, they also say that roughly half of the costs for the infrastructure are for less than 3% of the consumers. So that is because currently by law they have to interconnect very remote, have to interconnect everyone. And that is different for Horizon Power, who have more, who are operating and managing the network in remote areas and in more remote areas, even in Western Australia. So they have some trials into microgrids and standalone power systems that we're going to look at in a second. So looking at these long power lines that connect very few consumers, we have large network costs often, and they can be prone to risk like bushfires or storms. So by rethinking the way electricity networks are structured and thinking about local generation that could replace those long power lines, we could potentially lower the costs and also improve the supply reliability and safety of the network. And that is actually not just coming from outside. So there's already an uptake, and Australia is recording record numbers in solar rooftop installations. So a lot of people have photovoltaic systems now on their roof, and Australia is having more and more and like a large uptake in those installations, and is looking at record numbers in 2020 and probably 2021 as well. And if we look at the future plans of the network operators, often when they talk about future grids, that includes a more modular grid structure that has some interconnected network parts, but also some parts that are disconnected, and these are so self-sufficient, called microgrids. So basically smaller network parts that are isolated and can operate on their own, or so-called standalone power systems. As I already mentioned, there are some trials out there already. So these are just some examples that in remote areas in Western Australia are being employed. And throughout the year between 2020 and 2022, Horizon Power is installing roughly 50 standalone power systems. And the general setup for those standalone power systems are using solar panels as the main generation source, some kind of battery storage system with an inverter, and some diesel backup generator. So that's a typical setup. And the idea is to replace the poles and wires over the long run. I mean, these are just some examples, but one could also think of how do we plan a network in areas where there's currently no electrification yet. So especially looking at remote areas, basically the question is, how do we plan, how is the future network going to look like? And it's probably, or it might not be that the interconnected approach is the optimal way of doing that. So the research questions that I was facing, or that I was looking at, are basically how would such an optimized electricity infrastructure or network topology in particular look like? Where can we split consumers off the network? Where do we interconnect them into microgrids? And how can we even compare the different topologies and infrastructures? And then this also leads to how do we even represent such a problem? Okay, so on the representation of the problem, this is an example of a remote electricity distribution network that's somewhere outside of Perth in remote area of Western Australia. And we can see actually that there's no backup lines, so that's what we call a radial electricity network. And for me, in representing the problem, it just means that it's a graph that is a tree, so we don't have any cycles. And so when I want to represent the problem, I'm looking at a graph that consists of nodes and edges, or vertices and edges, and the edges that are representative of my power line connections, and the nodes are usually electricity consumers or substations. And then the next question was like, how do we evaluate such a system? So this is a very simplified approach. So that's just looking at the overall network costs to say over a certain time frame in years. That's here the Y in this formula. So how do we evaluate the costs of such a network infrastructure? So typically we have some kind of capital costs and operational costs. The capital costs are my infrastructure, or the cost for my infrastructure that I need to build this network. In this case, we have some kind of cost. So as soon as we split up a network part, so some consumer, we need to install some kind of source of generation. And I'm assuming the approach that Horizon Power is taking. So we have some kind of solar panel generation from solar panels with some storage and a backup system. And so that's a cost per microgrid that we have, and the microgrid has a certain size, and we have some diversification factor here that basically, or the idea behind that is that if we have a microgrid consisting of several consumers, then cost per consumer comes down because they are sharing their loads and they are sharing their generation. So that's a part of, so this basically is the cost that happens whenever we split a part of the network from the main substation connection. And we have some part of the costs that consists of the cost for the power lines. And we have some weighting factor. So that's basically for each edge that we have some specific costs, and in a simplified way, we could put a weight on the length or the cost of this of the power lines to increase further constraints. And I'm going to talk about that later in the talk. And then we basically also have the fuel costs. So if we want to maintain this network over a certain number of years, we have some costs of generation as well. But this is all very simplified, and a lot of it is hidden in those parts here. And obviously, if you go more, even more realistic, there's a lot more that you could include in this cost function. Okay, so a very first approach was using an evolutionary algorithm to find out what is the best network that we could, given a set of consumers and their loads and the distribution of them, so where they are placed and what their consumption is on average. The question is, so how do we solve this using the cost function that we have seen before? And due to the complexity of the problem, we used an evolutionary algorithm to do that. And the problem here is, so how do we, first of all, how do we represent the problem? What is the best approach? What are the best operators to do that? And what we have looked at is, so very basic approach, and this has been extended over the years, was to start the initial population with a minimum spanning tree interconnected system. So we have some kind of optimized approach of interconnecting consumers, which is actually not necessarily done in a real world electricity network. And then we used stochastic tournament, keeping always the keeping the best, making sure that we keep the best solution of each generation to pass it for reproduction and passing it on into the next generation. And we have some specific mutations that look at, if we represent the individuum as a graph. One of the mutation was simply splitting up network parts by removing an edge, joining isolated parts between, basically looking at the shortest connection between two groups of nodes that are already interconnected, and then joining them by the shortest in the shortest way. And then, so that was initially then used a combination of both of the mutations this is basically just to avoid stepping into some local optima, so having a larger step size in between them. That was an initial idea, and that's just a few years ago, but that was like one of the results, or one of an example of 300 consumers, where we can see the minimum spanning tree basically here, just yeah, very, very simplified in that way, and some interconnected parts and some completely isolated parts. For example, over here, that represent the microgrids and standalone power system, and some part that is still connected to the substation. So that is still our interconnected approach. And what we have seen is that the total cost, that the approach basically, that it converges to a number of specified for a certain number of isolated parts, so these are just the number of microgrids and standalone power systems, and that the overall cost is going down compared to the interconnected, already optimized approach. Okay, so that was just the very first approach, and as I mentioned before, we have used an evolutionary algorithm that we then further developed and looked at further looking into the interconnected parts of the algorithm and improved that, and I will explain a little bit more about how we did that. Another approach was also using an evolutionary algorithm, but a different representation of the problem. So in the end, we could also think of the problem, instead of like specifically looking at the interconnections between certain nodes, we could also think of, we could partition our problem space into subparts and basically look at the area. So let's say this is our area with some consumers distributed here. And we want to basically partition our space somehow and say every consumer that is in one of those partitions is going to be connected in one microgrid or a standalone power system part. And if we think about that problem in that way, then we have a range of different other approaches that we could use. For example, some standard clustering algorithm like hierarchical clustering or the density-based clustering that we could use. Or we've also used a k-means and k-means approach. And we have used some baseline approach, which is basically starting with an interconnected system and removing the most expensive edge, so the edge that comes with the highest cost. And the general idea was like, what approach works best on a range of problem instances, and is there some solution where we can say on this type of problem instances, or if we have specific type of problem instance given, then one approach is better than the other. Is there a trend? That was the question that we looked at. And are our evolutionary algorithms outperforming some of the standard clustering approaches if we assume that we have some kind of optimized approach of interconnecting them? And we looked at a different set of problem instances ranging from 10 consumers to 1,000 consumers, and we looked at different densities and different distributions of how the consumers are distributed in the area. Because if you look at real problem instances, sometimes you can see that in some areas that the consumers are located closer to a street or to some specific landscape, and so they're not necessarily just uniformly spread over an area. And so we looked at the different some different generated problem instances that were based on real network or real electricity consumer distributions and their loads, and looked at how these different approaches work on the different instances. Okay, so I have explained the very basics of the problem-specific evolutionary algorithms, where we have the individual is represented as a network. And I want to go a bit further into the evolutionary algorithm where we used a Quadtree representation. And then after we have found our optimal intersection of the area, we can then use a deterministic approach of connecting each part. Okay, so how the Quadtree partitioning evolutionary algorithm works is that we start with some initialization of some countries. So we basically, what is happening is that we split our area into 4 parts. And then these parts are further split until a certain number of maximum number of nodes in each part is reached. And that is done for further, like each part is like the split lines are generated randomly. And so we have each time we basically, even with the same split number, each time we generate some of those initial individuals, they have different, it's a different partition. And then we have to evaluate the costs. We transform that into our network part. So we interconnect each network, each part in each each subpart, and then we evaluate the total costs as I've introduced, and then we basically go through several mutations. So one of them is after selection, we go through the mutations if that either is we divide one of the sections further. So that would be, this is just one example. We can merge sections together. We also introduced some labels for each part, so you can see the ones and the zeros here. And this basically means that if we have the same label on both sides, and it means that this interconnection line is open, so it means that we can merge two of those sections together, or that's how they are viewed in the, like when we look at how we put those consumers together. So by introducing these labels, we have another mutation that switches those labels between on and off. So 0 and 1 stands for on and off. And so we change those labels randomly, or we flip just one of the labels, and then we also combine the different mutations without having any cost evaluation in between. And we do that until, for a number of generations, there's no further improvement seen anymore in the total costs. So that's roughly how the algorithm works. So over here, this is probably better to explain how we merge the different sections. So if this and this one is both true, so if both is 1, then we can interconnect this part with this one. And so we get all sorts of possible and feasible intersection of the area. Okay. Okay, so the question is, how do we connect the nodes in the parts that are already grouped together? And I'm going to go through that. I don't want to jump around too much, but before I go into that part, which is a whole another area, I want to just quickly give you an overview of some of the results we got for the different algorithms. And this is over all instances, the minimum, maximum, average, and median cost reduction compared to an interconnected system. So the higher the number of percentage, the better the algorithm has worked on average. And some of them seem to be very similar, but we have to look closer into the different problem instances. And these are just 2 examples. So what we can see on average, that the removing edges like baseline approach performs worse, and that our evolutionary algorithms usually perform better. And we've done some statistical tests run on that as well. To be precise, the Wilkinson design rank test, and found out that the evolutionary algorithm outperform the other ones on most problem instances, but not always the same one. So if we have a look at, for example, the 50, this is an instance of size 50, so there are 50 consumers. They are uniformly and normally distributed. And while we can see the red line is the specific problem-specific evolutionary algorithms. The yellow line is the removing edges one. It changes if we look for the different distributions of the consumers. And what I've seen from most real-world cases, the normally distributed one is closer to the real-life cases in most instances. And for 50 and also for 1,000 size instances, we can see that usually the problem-specific algorithm outperforms the other ones on average, and on the x-axis we have the different densities. But if we look at the uniformly distributed ones, we can see that the evolutionary algorithm here for very sparsely distributed consumers, so we only so they're spread over a large area, we have the specific problem-specific evolutionary algorithm is performing best. But then that changes later on if we look at more densely connected consumers, and it's hard to see in this one, but they are the Quadtree-based approach, and also the density-based or hierarchical clustering are really very close together. Yeah, and they are on these very, very large instances of 1,000 consumers. For more densely connected nodes, they outperform the other ones. Yeah, so that's what we found. So, okay. Is there a question?
太棒了，这大概是几点可以呢？
Okay, I'm just gonna continue that. All right. So these are just some results giving yeah, before we actually look into how we actually interconnect those parts. And so let's have a look closer at how we actually look at interconnecting the nodes within one section once we have determined that, because that is basically what we use for the Quadtree evolutionary algorithm approach, but we also use that for the standard clustering approaches. So they basically just give us the clusters, and we still have to determine how to interconnect actually the consumers in those areas. And for that problem, we looked at the Euclidean Steiner tree problem. So basically a minimum spanning tree problem where we have some nodes in the Euclidean plane, but we are allowed to add further nodes. So for example, if we have only 3 nodes, this is also called this extra node that we can add is called the Fermat-Torricelli point, and we actually know where it sits. So it is exactly in the middle. It is connecting those 3 points, and between each of the edges we have 120 degrees. And for 4 nodes, and minimum Steiner tree would look like this, and for 6 nodes that are distributed like that, we have actually 1, 2, 3, 4 further interconnection nodes. And these interconnection nodes, they are called Steiner nodes. So basically we have some nodes that are called terminals, and we want to find the minimal interconnected network, minimizing the distance in this case, that might include further so-called Steiner points. And despite that, it sounds like yeah, it's very similar to the minimum spanning tree, but it is much more complicated actually calculating the optimal solution, and that is despite we know a couple of interesting properties for those points. So actually we know the maximum number of Steiner points if we have a Steiner minimum solution is n-2 if we have n nodes to connect. we know that we always have this 120-degree condition for a Steiner node between all of the edges that we connect through a Steiner node, and we know that so we know that this degree condition is what we're going to use later on. And we also know that a Steiner point is adjacent to exactly 3 other nodes, and in a minimum Steiner tree there's no degree that is higher than 3. So we have a lot of properties, and there are several more ones, and still it's an NP-hard problem, so just looking at that part. So we need some kind of approach that we can use within our evolutionary algorithms for each of the interconnected parts. And the approach that we have used is an iterative approximation using some of the properties that we have just seen. Mainly the one that we know about the degree condition. So the steps in an iterative approach are basically, we can start with the minimum spanning tree. And if we consider later on further constraints and obstacles, we can use a minimum spanning tree that uses a shortest path algorithm that goes around some of the obstacles, but I will come to that later on. And then we basically repeatedly insert nodes where we have an angle that is less than 120 degrees. And if we do that repeatedly, removing the edges that have been there before, sometimes, well, in some cases, it converges to the actual minimum spanning tree. But in some cases, it looks different than the optimal solution, but we get an improved approach for interconnecting these nodes that approximate the Steiner minimal solution. And this is just as an example, some case where it's actually like the first approach looked like we're gonna always get the same solution, or that was like, in this case with the 4 nodes, we got the exact solution with this approach, or something that converges to it. But there are some cases that for these grid structures, for example, where the iteratively approximated solutions might look very different to the actual solutions. Okay, so that's so much on the Steiner tree problem. So we're going to use that for the to further optimize the interconnections in the connected parts. And now, while this is already a complex problem, we want to be able to further consider constraints that we might have in a network. So for electricity networks, we might have some areas, and this image here is just an example. It's not actually the real world constraints for this network. But we might have areas where we can't build any power lines through, so-called solid obstacles. We have to go build our network around them. Might be private property or nature reserves or lakes or other areas. We might also have areas that maybe we can build through, but it comes at a higher cost, or we can implement that in our cost function as a higher cost. So for example, areas that are harder to access or very risk prone, and we want to consider that within our cost function. So we need an approach that can also consider obstacles. In order to do that, so this is just an example where we have a Steiner minimum tree that considers soft and solid obstacles. So if, for example, we have the optimal or the Steiner minimum tree would connecting the blue nodes, which are our terminals, looks like this, and the black nodes are my Steiner points that are inserted. Then if we consider those solid obstacles here and the soft obstacles, an approach might now, like the solution, Steiner minimum solution, might be tortured in those parts. So we have more points, and we have we have here these could be, we call them obstacle corner points, but you could consider them as Steiner nodes as well. But we distinguish between them in our approach. Okay, so in order to do that, basically we have to look at a new problem definition. So we consider a set of n terminals and O simple polygonal obstacles with some crossing weights. In our case, we just assume that if we cross a soft obstacle, that is that it comes with a homogeneous weight applied to that connections that are within the obstacles. And we want to find a connected network that spans all the terminals but has minimum total length, and can also include further nodes. Okay, so one approach to do that, and this can be read up in the in one of the papers we did for the GEC conference this year, is to use another genetic algorithm for finding those optimal interconnections. And I'm not going to go into detail here because I think I would go over time otherwise. But the basic idea is that we can move, use a specific representation of our problem where we have the Steiner, so the terminals are set, but we can move the Steiner nodes, and some of the mutation is actually moving the Steiner nodes from one place and shifting it slightly. But also we could switch on and off the so-called obstacle corner nodes. So this representation here, 0 stands for that we don't use a specific obstacle corner in our tree representation, and 1 stands for that we would use that. And without going into much detail, we could find that we have different mutations and crossover. And for this approach, I'm just going to show you some of the results. We could see that we could improve existing approaches, or we can improve the solutions to some of the existing approaches going around solid and soft obstacles on average, and having that we can actually find that our genetic algorithm finds better solutions to the problem instances that were tested before. But this would mean that we use another genetic algorithms within our evolutionary algorithm approaches. And so if you are interested in that, we can talk about this approach later on. But what we used within the algorithms for planning the electricity network is an iterative approximation as a baseline. And so this is basically what I've already mentioned before. So we start with a minimum spanning tree that considers obstacles by using a shortest path algorithms around obstacles, or considering the weights for soft obstacles. And then we repeatedly insert a Steiner point at the small angles, so similar as we have done before. And now we have 4 different cases that we need to consider. So either a Steiner point is inserted and the position is added. And then it means that the 2 edges that have been at this, that build this angle before, are removed. But it could also be that the Steiner point would be inserted into a solid obstacle this way, and then the Steiner point is not introduced. We could have, we could also have that the current state, that even though we have a small angle, that the current state is actually the smallest approach. or we could have a Steiner point inserted in within a soft obstacle, if that means that this interconnection line then is shorter or comes with a lower cost. So the least cost connection is selected in this iterative approach. And this is some of the some example problem instance where the dark areas, those are my solid obstacles, and the light areas are the soft obstacles. And the iterative approach in this is kind of one of a more extreme case, could look like that, while you can, and the like the genetic algorithm approach would be much more optimized in that way, because it's able to to locate those Steiner points here, while this iterative approach wouldn't be able to get that. But overall, especially for random problem instances, we find that the iterative approach is a good approximation. Okay, so just for looking at some of the results for solid obstacles only, we can see that our genetic algorithm that I have only briefly touched can go find complicated solutions that go around and in between obstacles like this, and that we can see that it converges. So I'm not going to go into much detail here, but we basically found that the genetic algorithm works quite well for those approaches. And we have looked at, and this might be interesting for future work, also looked into increasing rates of obstacles. So if we consider soft obstacles, and we have a weighting factor of 1.1, and then we increase that further into up to 5 times as much, how does the solution change? And at this weight, for example, it would be the same solution as almost as having solid obstacles, apart from the fact that we couldn't go in to reach those nodes. Yeah, so this might be for the future, might be interesting to look at. But the basic, so what we have basically done for the electricity distribution networks is using this iterative approach for each connection here. And so this might be, for example, a solution. This is a problem instance with 450 electricity consumers and some solid obstacles in these cases. So these are here the gray areas, or in this case the dark red areas. And what we basically found is, even when we insert the application that considers those solid obstacles, that the evolutionary algorithm still performs well on those problem instances, and that it is able to handle large cases, like with a couple of hundreds of nodes. Considering those obstacles in these cases, as we can see here, going around the obstacles when we interconnect them using this iterative approach for each part. And this is and this works as well for the Quadtree based approach, where we use that as a representation of the network, as well as for the problem specific evolutionary algorithms, when we adapt it in a way that we include the consideration of obstacles through different mutation. So for example, when we connect two different parts, then instead of just connecting it through a straight line, we have to use the shortest path algorithm to move around the obstacles, for example. Or when we remove the highest cost edge, we might not just remove this one edge, we might remove a connection that goes around an obstacle. So this is just roughly explaining the idea of what we have done for that approach. And what we could see is that both evolutionary algorithms are performing outperforming our like baseline approach, where we simply remove the highest cost edge. And we could basically, what was interesting to see is that we can, in this way, using this iterative approach for the Quadtree based algorithm and using different mutations for the other evolutionary algorithms, that we could incorporate those constraints in our network planning approach. Okay, to just come to an end, just looking for at further possibilities. So I know I've only talked about electricity distribution networks, and so looking further into those in the future, one could consider obstacles with non-homogeneous weights. So we could have step functions or distribution functions of weights within the soft obstacles. We could also consider already existing network parts. Let's say we have some network parts that are already there and that aren't very old, so it might be cheaper, instead of removing them, to keep them. In the good thing about an evolutionary approach is that it can be adapted to those considerations. And we can also within the cost function implement a way to determine the optimal placement and sizing of there's a word missing, I'm sorry, of the generation sources in the interconnected parts. So while I have talked about electricity networks, I have recently also read a paper where the authors are considering the decentralization of water supply networks. Or I have also talked about, with people about road clearance services, where maybe not in Australia, but when streets are blocked by snow piles or something like that, and we consider how we want to clear these areas, that we also could look at a network that we might want to split up into different service areas, and also have further constraints, maybe roads that are blocked where we can't go through. There's the paper that I briefly mentioned before, where the application were communication networks in those areas. So I think that in general, the idea of looking at an optimized network and maybe splitting up the networks under the consideration of obstacles can be helpful in many areas. And yeah, maybe you have some further ideas as well. And what I thought about maybe doing further is in looking at different approaches to implement in the evolutionary algorithm, for example, a multi-objective approach that can consider different objectives. Like one objective could be avoiding the obstacles, and another one finding the best part. Or this could be further adapted to whatever the needs basically are, and to make it more explainable in what parts of the cost function might be more important depending on the approach or the application. And another idea was to increase the weights of the obstacles, of the solid obstacles, when we actually have solid obstacles, but we basically make them soft obstacles in the beginning, or completely ignore them, and then include the weighting of the obstacles within the evolutionary approach, and increase them going through the algorithm. Like this could be incorporated within the evolutionary algorithm. But those were just some ideas, like what could further explore. And I don't know if I get the chance to do this, but if you have further ideas, I would still, like to hear them. That's it from my side. Thank you.